Okay, so hi everybody. So let me post the link where this is being streamed. Okay, so hi everybody. So let me... Okay, so that's the link. Okay, so it's lecture 14. Can everybody see the page? Is this better than what I usually do, or is it just annoying? I'll just do it the usual way. Okay, so it's lecture 14, and oh, I see. Somebody said it is better. Okay, let's try this. So it's lecture 14. So it's another lecture on counting. So let me just briefly recall what we did last time. So last time we did basic counting techniques. And this could be organized into a series of rules, which we called the product rule, the sum rule, the subtraction rule, and the division rule. And then we use these to count various interesting collections of objects. And two particularly important cases that are going to come up again and again and come up a lot in math are permutations and combinations. So two important cases. Are permutations. So Pn comma R is the number of ordered R sequences of n objects. And this number has a formula. This is n factorial divided by n minus R factorial. And these are called permutations. And then a related but different type of count is to count unordered subsets. So CNR combinations refers to the number of unordered R subsets. So the first one was ordered of n objects. And the number of combinations is n factorial over n minus R factorial. Sorry, that doesn't look very good. You write it like this. Is n factorial over R factorial times n minus R factorial. And there's a relationship between these numbers, which is actually how we derived them, which is that the number of permutations is equal to the number of combinations times R factorial. And we derived this using this division rule, which I stated in terms of bijections, not bijections, in terms of functions and m-to-1 functions last time. But there's actually a very simple, intuitive way to state this, which I'll just mention now. It's just saying that if you want to count sheep, suppose you want to count sheep, and you know that every sheep has 4 legs, then one way to count the number of sheep is to count the number of legs and divide by 4, right? So the division rule is just a fancy way of saying to count sheep, count legs and divide by the number of legs per sheep. Okay, so that's the division rule is just a fancy way of saying that. And that's how we got this relation. And really, maybe even more importantly than these rules, there were two, I would say, key principles, which are the key principles of counting that were kind of in the background. So the first principle was that to count a collection of objects, it was helpful to specify a process for uniquely specifying an object. So to count objects in a collection, define a process. And by process, I just mean a sequence of choices. For constructing an object from the collection. So define a process uniquely specifying an object from the collection. So we saw this over and over again. And really, there is an even deeper underlying principle, which is in some way the single most important principle in counting, which kind of defines this whole area of math. And that is the fact that if you have two sets and you have a bijection, they have the same cardinality. So if F mapping A to B is a bijection, then those two sets have the same cardinality. Now, we've already seen this in the first 5 lectures, but really this is what underlies all these counting rules, actually, in a way, because, I mean, okay, so the simplest in the sheep context, this is just saying that if you want to count the number of people in a room, you can count the number of heads in the room because every person has one head and the head uniquely defines a person. The number of heads is there's a bijection between, the heads and the people, right? So because nobody has 2 heads, right? So to count people, count heads. So implicitly there's a bijection between heads and people. And I can put 2 arrows to indicate that this is a bijection, to say that this is invertible. So there's a. And really, in terms of bijections, even the first key principle is really a statement about bijections, because what we're really doing implicitly, so in 1, what we've been doing is we're actually implicitly setting up a bijection between ways of making choices in this process for specifying an object and, the objects in the collection. And again, this is a bijection. So this is really the most important thing about counting. You could even say counting is the art of finding bijections between, a complicated set of objects and a simple set of objects. So that's a recap of what we did last time. Any comments or questions on that? Okay. So this time, what are we going to do? We're going to do 3 things as usual. I'm going to talk about a connection. So I'm going to focus quite a bit on these permutations and combinations. There's a very important connection to algebra that comes up that maybe you've already seen called the binomial theorem. Then I'll say a bit more about permutations and combinations in the context of the binomial theorem by proving some algebraic identities using counting. So I'll call these combinatorial identities. So I believe this is the content. This is the content of section 6.4. And then finally, I will generalize permutations and combinations to well, to count to count arrangements of objects with repetitions. So okay, so let's start with binomial theorem. Okay, so the binomial theorem is, let's start with an example. Okay, so everybody presumably knows this formula. If you have two variables, x and y, then x plus y squared is x squared plus, sorry, plus 2xy plus y squared. I want to write it like that. And maybe, you know, less obvious is what's the formula for x plus y cubed? Or I don't know, what about x plus y to the 10? And these are expressions that come up a lot in mathematics. And it turns out the answer, so this is an algebra question, right? But the answer to how to solve this question is related to counting. So let's solve this question using counting techniques, right? So so observe that if you look at x plus y cubed, then this is just x plus y times x plus y times x plus y. And I'm going to do something that looks a little silly. I'm going to just expand this out in all the terms, just using, you know, FOIL or whatever it's called, like just how to multiply polynomials with parentheses. So if I multiply this out, then how should I go about it? Well, I don't know. Any thoughts on how to organize the expansion?
Maybe start with the distributive property for the x's first.
Okay, start with the distributive property for the x. So so I'm going to look at terms that contain this x. So it's going to be x times this whole expression. And then I can apply the same reasoning in here, right? This expression is going to be this x times this whole expression. And then there are going to be two terms, the x term and the y term, right? So if I look at those terms, I'm going to get x, x, x plus x, x, y. Okay. And then if I now, you know, look at the, I mean, I need to be a little bit organized about how I do this, but okay, if I just do this in some kind of well, okay, not entirely arbitrary, but one way to do it, you would get terms like x, x, x plus x, x, y plus x, y, x plus x, y, y plus y, x, x plus y, x, y plus y, y, x plus y, y, y. If you keep applying the distributive property, this is what you'll get. You'll get 8 terms. Now, I kind of just did this in kind of a, you know, whatever way I wanted, but now I want to observe the pattern in these terms. So what's the pattern? So what I'm going to do is I'm going to give each of these copies of this expression x plus y a name. So let's call this S1, let's call this S2, and let's call this S3. So now the thing to observe is that each term above looks like this. It has either an x or a y from S1, the first parenthesized expression. Then it has an x or a y from S2, the second expression. And then it has an x or a y from S3. Okay, so each term above, so I haven't grouped the terms. So obviously I can collapse these terms because some of them are actually the same. But before doing that, there are 8 terms, and each one is, it can be uniquely specified by choosing either X or Y for the first parenthesized expression, then X or Y for the second one, then X or Y for the third one. Okay. So, so what does this tell us? Well, okay, so first of all, the number of terms before grouping any like terms. How many should there be? Well, there are 8 of them, but based on this little calculation, I can uniquely specify a term by making each of these choices, right? And for each choice, I have 2 options. So the number of terms before grouping is 2 times 2 times 2, which is 8. Okay, we knew that just by doing it. Right? Because this is essentially by the product rule, because I had 2 ways of making each choice. Okay. But now, I can notice that actually a lot of these terms are the same, right? Because, I mean, these variables, by the commutative law, the order in which I multiply them doesn't matter, right? So there's this observation here, which is, x, x, y is the same thing as x, y, x is the same thing as y, x, x, and these are all equal to x squared y. So if I apply this and I group the terms, so let's call this step the step where I group the terms. Sorry, that's not very legible. Then, okay, so this we have to be a little careful about. So let's think about this. So okay, so the way I'm going to group the terms is by counting the number of x's in them, because that's what ultimately tells me which terms I can group together. If 2 terms have the same number of x's, I can group them together. So observe that the number of terms with, or maybe I should move this down here. With 3 x's is, well, I don't really have any choice. I have to choose x in the first one, I have to choose x in the second one, and I have to choose x in the third one. So this is just 1. The number of terms with 2 x's now, this is where permutations and combinations come in. So how many ways are there to choose a term with 2 x's?
C of 3, 2.
Okay, and why is that?
Because we are basically picking 2 of S1, S2, S3 to contribute SS2, and we're seeing how many different ways we can.
Yeah, that's a good way to think about it. So the number of terms with 2 x's is the number of 2-element subsets of the set S1, S2, and S3, because I'm picking 2 expressions to put x's in, and I don't care about the order. That's the key here. So that's why I have subsets. And then this is just C of 3, 2. So the key thing, the key step here was this equality. And in this equality, really, I'm saying, hey, there's a bijection between the things on the 2 sides. Right? So that's why I kind of said counting is all about bijections. There's an implicit bijection here. And I did in the last lecture, we did this. This is just the number of combinations. And so similarly, then the number of terms with 1x is the C31, the number of ways to choose a one element subset of S1, S2, S3, because I just choose one clause to put the x in. And then the number of terms with 0 x's is just C of 3, 0, which is 1. Okay, so I should compute these numbers. This is 3, and this is also 3. And so now, so let's pause here. Anybody have any questions about this?
Can you go back to explaining the part where you were explaining, or can you revisit it when you said the number of terms with 2x's equals the whole explanation? Yeah.
Right. So remember, each term comes from 3 choices, right? You have to choose an x or y from S1 and an x or y from S2 and an x or y from S3. So now if I have to choose 2 x's, what I'm claiming is I can formulate that differently. I can say, hey, I have to choose 2 out of S1, S2, S3, 2 of those to make x's, and I'm going to make the last one a y. But that's exactly choosing a 2-element subset of S1, S2, S3. Right? There are 3 clauses, and I have to choose 2 of them, and the order doesn't matter. That's why it's a subset.
Okay, so okay.
Does that answer the question?
Yeah, so you're basically saying I just have to figure out which combination, I had to figure out the combination sets, basically.
I have to figure out which clauses the x's are going to come from.
Okay.
Are they going to come from S1, S2, or S2, S3, or S1, S3? Those are the only options.
Professor?
Yes?
I understand the step of choosing like x from 3 different, 2x from 3 different S1, S2, and S3, but I don't see how the 2 elements come out, 2 element subset. How is that description working?
Oh, well, so the way to think about it is I have these 3 clauses, right, up here. And what I have to do is I have to say, well, 2 of them are going to be x. So I could either do these 2 are x, or I could do these 2 are x, or I could do these 2 are x, right?
Okay, so you are basically choosing like a subset called S1, S2 from a big set of S1, S2, S3.
Yeah, exactly.
Okay, thank you.
So for the terms with 2 x's. So these are the possibilities. So that's the correspondence. Implicitly, that's the bijection between subsets of S1, S2, S3 and terms with 2 x's. Those are not literally the same thing, but there's a bijection between them. So anyway, the conclusion now is that after you group the terms, so after grouping the terms, you have x plus y cubed equals, I guess, the number of ways of choosing 3 x's, which is there's only one way. So that's the first one here. So yeah, I should say that this is really the number of ways of choosing all of them to be x's, and there's only one way to do that, right? Plus the number of ways of choosing 2 x's plus the number of ways of choosing 1x. And remember, anything that's not an x is a y. Plus c, sorry, no need for parentheses. And okay, this is now x cubed plus 3x squared y plus 3xy squared plus y cubed. So we studied the terms before grouping. This is the part that might be different from high school algebra. You're just tempted to always group the terms, but it's actually important to look at the pattern in the terms before grouping, and that's where the counting comes up. So after grouping, you get this formula. And this is a special case. So we solved this case of x plus y cubed. But now you see the general pattern. Let me write the theorem and the proof. It's a very important theorem. So before the theorem, let me introduce a alternate notation, which is used throughout math. We use this parentheses with n above and r below to denote C and R because it comes up a lot. And this is read n choose R. And this is called a binomial coefficient. And now the associated theorem, which I'll now state with the new notation, is the binomial theorem. And the theorem says if n is any integer bigger than 1, then if you have an algebraic expression like x plus y to the n, then it's equal to n choose n times x to the n plus n choose n minus 1 times x to the n minus 1 y plus n choose n minus 2 times x to the n minus 2 times y squared dot 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 all the way up to n choose 0 times y to the n. So this is a generalization of what we did for cubes. And in summation notation, you can write this succinctly as this is equal to summation as r goes from 0 to n of n choose r times x to the n, x to the r times y to the n minus r. So that's the statement of the binomial theorem. The reason it's called a binomial is, there are two variables in the expression to the left. I mean that's just sort of an etymological reason why it's called a binomial theorem. So any questions about the statement of the theorem before I proceed?
Can we use a similar kind of thing for like more than two variables?
It's a great question. Can we use, does a similar thing work for more than 3 variables? So the answer is yes, but it's more complicated. We won't explicitly do it, but in the next lecture, I'll essentially teach you enough about counting that you can do it by yourself. So this is called the multinomial theorem. And you can get this using methods from the next lecture. Indeed, you can study any number of things using counting. But let me now give you the proof of this theorem. It's a great question. Okay, so let's see the proof. So so I'll write it this way. So the coefficient of so let R be some, so yeah, I should say what n and R are. So let n be some positive integer and R be some integer less than n, but at least 0. So now what I'm interested in is, the content of the theorem is the left side is a sum of 2 variables to a power, whereas the right side is a sum of monomials. So it's a sum of things that only have multiplication, right? Like each of these things is called a monomial. I guess I shouldn't use the same color marker. So this is called a monomial because it doesn't have any addition in it. And this is called a binomial because it has 2 terms that are added. So now to prove the theorem, what I need to check is, so clearly if I expand the left-hand side, I'm going to get and I collect the terms, I'm going to get a sum of monomials. And the only question is, what are the coefficients in front of the monomials? So I'm now going to study the coefficient in terms of x to the r, y to the n minus r. So observe that the coefficient of x to the r, y to the n minus r in this product, x plus y, dot, 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 multiply this n times. Is the number of ways right, or let's put it this way, is the number of terms before grouping with exactly r x's and n minus r y's. So with exactly r x's. Okay, so the terms before grouping are really strings in x and y, right? So these terms before grouping are strings in x and y with n letters. Okay, but now, this is equal to the number of r subsets of n, which is equal to the number of r subsets of 1 through n. And here again, there's an implicit bijection. It's the same as last time. And the bijection is, well, the subset tells you the position of the x's, right? Okay. So often in these kind of proofs, you don't explicitly specify the bijection, but I'm doing it just to be clear. And then we know what this is. This is equal to n choose r. And that's it. That's the whole proof. So I would say the creativity in this part is thinking of looking at the terms before grouping, right? So this is one very interesting sort of creative part. We don't normally do that in algebra. And then the second creative part is to notice this bijection. So really, we're really realizing that these terms have exactly the same structure as just the R subsets of 1 through n, and we know what that is essentially. And that's the proof of the binomial theorem.
Could you move a little bit up to the sigma sign, the final conclusion?
Yeah, so the content of the theorem was that the coefficient in front of x to the r, y to the n minus r is n choose r. And we just proved that. Observe that the coefficient of this thing that I care about is, the content is, I turned it into a counting problem. It's the number of terms before grouping with exactly r x's. And that's the same thing as strings in x and y with n letters, which is the same as the number of those things is the number of R subsets of 1 through n, because there's a bijection, and that's n choose r. So it looks like nothing happened, but really what I did is I realized that these three different things are all in bijection with each other, or at least these two different things. Any comments or questions about that? Okay, so what they're saying is that even inside algebra, this counting stuff is kind of hidden. And in higher algebra, this comes up a lot. So it's kind of definitely if you're a math major, this is going to come up a lot. Okay.
I have a question.
Yes.
So in the previous example that we had, where we had x plus y to the power of 3,
Yep.
we kind of like, we didn't expand it, but we just showed like those 3 products. Each term, right? If we add all those up, it just equals to 6. And so that's what we explained in your proof for the binomial theorem, right?
Well, it doesn't equal 6, right? So like, okay, let me explicitly point out the grouping, right? So what are the groups? So there's one term with 3 x's. Then there are 2 terms with 2 x's. Sorry, 3 terms with 2 x's. This, and this. And then there are 3 terms with 1 x, namely this, and this. And then finally, there's 1 term with 0 x's. And so what the proof is saying is, first expand the terms before grouping, and then group them by the number of x's. And when you do that grouping, the number of times a particular term appears is exactly given by this counting problem. So really what I'm doing here is that the yellow terms correspond to this. Sorry, that's not what I wanted to do. The yellow terms are these terms, and then the green terms are these terms. Does that make sense?
Yeah.
Yeah.
Yeah, that makes sense.
So the proof is actually just the same thing. I'm just saying, hey, you can do this in general. Now when you do a proof like this, it's very important to write very carefully. Okay. So, I mean, while the logical structure of these counting proofs is less clear, the writing, everything has to be very precisely specified. And, if you're in doubt about when 2 things are equal, ask yourself, what is the bijection? Okay, so now we're going to build on this idea to prove some more interesting algebraic formulas using counting. So this I'm going to refer to as combinatorial identities. Combinatorial is just a word that means like related to counting in math. Related to counting and bijections generally. Okay, so let's start off with an easy one. The first one is if n is bigger than 1 and r is between 0 and n, then n choose r. Sorry. Is equal to n choose n minus r. Okay, so I mean, okay, there are 2 ways to prove this. So there's the first proof, which is boring and algebraic. And that proof as well, let's just write out the formulas, right? This is equal to n factorial over r factorial times n minus r factorial. But then I can swap the order, right? This is n factorial over n minus r factorial times r factorial. But this is the formula for n choose n minus r, right? Because r factorial is n minus r. Okay, so this is not a hard fact, and there's an algebraic way to prove it, but there's a really cool way to prove it using bijections. The combinatorial identities are essentially formulas proven using bijections, or formulas proven using counting. The second proof, which is based on bijection, is I'm going to count I'm going to count Yeah, I'm going to show that these numbers are counting something, counting a collection of objects, and there's a bijection between what they're counting, right? So let A be the collection of subsets of n of size R, and let B be the collection of subsets of n of size n minus R. Okay. So we know that the cardinality of A by definition is n choose R, and the cardinality of B by definition is n choose n minus R. But now I'm going to show that these two things are equal by finding a bijection between these sets. So can anyone think of a bijection between these sets?
You can take the complement of S.
Yeah, you can take the complement, right? So observe that F going from A to B by F of a subset is just the complement of that subset. So it's 1 through n minus the subset is a bijection. So this is easy enough that I'm not going to formally prove it, but you know, the picture associated with this is you have these elements 1 through n, and then you know a subset of this is just you color in some of the squares, and then you know if you just map that to its complement, then you can invert that in the obvious way. There's a 1-to-1 and onto function. So then the conclusion is that the cardinality of A equals cardinality of B. So n choose R equals n choose n minus R as desired. Okay, so I proved that these two sets have the same cardinality by explicitly showing you the bijection, right? For every set in A, every set in A uniquely specifies a set in B and vice versa by taking the complement. So the creative step here was realizing this. And you know I mean the key thing is that this is a bijection. So any questions about this? This is kind of the easiest combinatorial proof. You can also think of it like, you know, here are two different ways of choosing an R subset of 1 through n. One of them is to choose the elements in the subset. A different way, which is equally good, is to choose the elements that are not in the subset. Right? Two different processes for counting the same collection of objects.
How do we know when we're writing a combinatorial proof in general, should we always explicitly describe the bijection and show that it's a bijection?
No.
How do we determine
right. So that's part of the, I guess it's kind of like that's part of the learning how to write proofs. If you're in doubt that what you wrote is not clear enough, add more detail.
Awesome. Thank you.
I'm going to actually show you a few proofs with less detail that are also acceptable just in a moment. But it's a great question. Okay, let's do a second example. Here's example 2.
A quick question, like what we prove in class, for example, with this one, on the quiz, can we use like any of these proofs to prove it, or can we directly use it?
Well, if you cite it, you can use it. If you state exactly what you're using, you can use it. That's a general principle in the course.
Is that a minus S after the F of S?
Yeah, minus S. So it's the set difference. So you take all the elements 1 through n and remove S. So this is the complement of S. Okay, so now let's look at a slightly more interesting one. Here's the claim. So if n is a positive integer and R is between 0 and n, then 2 to the n is equal to n choose n plus n choose n minus 1 all the way up to n choose 2 plus n choose 1 plus n choose 0. Oh, sorry, I guess there's no r anymore. So it's just this. So this is a summation. Or r goes from 0 to n. Of n choose r. So if you add up all of these binomial coefficients, these are called these are also called binomial coefficients. Then you just get to the end. Now again, there are two proofs of this. There's a boring algebraic proof, which I'll skip. So, or I'll just tell you what it is. So proof 1, algebra, is just plug x equals y equals 1 into the binomial theorem. Right? So if you go back into the binomial theorem here, if you just plug in 1 for x and y, right? Then you just get this, right? You get 1 plus 1 to the n, namely 2 to the n, is equal to summation n choose r times 1, which is what we wanted to prove. It's okay, not hard to prove algebraically once you have the binomial theorem. But let's see a combinatorial proof of this. And I guess this method could be called maybe double counting or counting in two ways. Okay, so what I'm going to do is I'm going to define, I'm going to count the number of subsets of 1 to the n in two different ways. We will count the number of subsets of the set 1 through n in two different ways. Okay, so we already know how many subsets there are of 1 through n. I think we did it last time in the lecture. So how many subsets? So I mean, okay, let me just spell it out, right? So method 1. So a subset S of 1 through n is uniquely specified by the following choices. By choosing whether 1 is in the set, 2 is in the set or not, all the way up to n is in the set. This is a kind of new notation I'm introducing. It's okay for you to use it in the course if you want, since it's kind of extremely clear what it means because these are choices. So by the product rule, there are 2 to the n ways. Okay, any questions or comments on that? That's something we kind of did last time. It's a very simple way to count. But now here's a weird way to count, method number 2. Okay. So what we're going to do now is we're going to choose a subset in a different way. We're going to first choose the number of elements in the subset. Okay, so a subset S contained in this set is uniquely specified by the following steps. Choosing an integer r between 0 and n, and choosing a subset of R of S with exactly R elements. Right, so there's a different way of uniquely specifying a subset of 1 through n. First choose the size, and then given the size, choose the subset. So now, if I think about it, I really shouldn't apply the product rule here. So how do I now count based on these rules?
This would be the sum rule, right?
Why would this be the sum rule?
So we notice that like once we once we choose R, for any two particular values of R, clearly we aren't going to have any overlap between, say, sets of 2 elements and sets of 3 elements. They're just completely different things. So we've got a bunch of distinct sets, the sets with R equals 0, R equals 1, R equals 2.
Great. Yeah, that's a great explanation. So once you choose R, these are all disjoint families of subsets. So really what I'm saying here is given R, choosing a subset of that size. And so by the sum rule, so how many choices are there for the second step? Well, there are n choose R choices. And this depends on R. It's different for different Rs. So now the total number of choices is the sum of all of these things. So by the sum rule, the total number of choices is the sum. But now these two things have to be equal, right? I just counted the same set. The punchline is that these have to be equal. So that's the proof. So I proved this without doing any algebra. That's the beauty of combinatorial proofs. There are actually a lot of algebraic identities in higher level math that nobody knows how to prove them using algebra. You can only prove them using counting. So thus, this is not one of them, since this is not too hard to prove using algebra, but there are many. Any comments on this proof or questions? It's a very powerful method, counting 2 ways. It seems a bit sneaky, right? You want to prove that 2 numbers are the same, so you count the same collection in 2 different ways. And implicitly, what you're saying is that there's a bijection between these 2 schemes of making choices. That's the bijection. Any comments or questions on this? Great. Somebody accidentally proved it while doing the homework. Great. Yeah, it's always great to rediscover math on your own. Okay. Let's do one more example of a combinatorial proof. So this is a very important identity. And before doing it, let me show you a motivation. Or let me just prove it. So this is called Pascal's identity. And what it says is if n is a positive integer and R is at least 1 and at most n, then n choose R is equal to n minus 1 choose R minus 1 plus n minus 1 choose R. So before proving it, let me show you what it looks like graphically. It gives you something called Pascal's triangle. So what you do is you list out the binomial coefficients. So for n equals 0, there's only 1. For n equals 1, sorry, that's not n equals 0. That's n equals 1. For n equals 1, oh no, that's n equals 0. Sorry, for n equals 0 is only 1. For n equals 1, there are 2. X plus y is just equal to x plus y. And now you do this for n equals 2. The coefficients are 1, 2, and 1, right? Now, what this identity tells us is that to get a coefficient at the next layer, you just add the coefficients above in the previous layer. So 1, 2, 1. So what this is saying is the middle thing here is 2 choose 1. And what the identity is saying is that 2 choose 1 is the same as 1 choose 1 plus 1 choose 0. Now, the beauty of this is that this is actually how you compute binomial coefficients on a computer, is that now if you want to compute the next row, you just put ones at the end, and now you just fill it in by adding the numbers above. So you get 3 and 3. That's correct. And then if you want to do, so this is n equals 3. If you want to do n equals 4, the general rule is you put ones at the end, and then you just fill in the rest by adding the 2 numbers above. And lo and behold, you get the right answer, right? You get 4, 6, 4. So this is actually a recursive definition of the binomial coefficients. And the beauty of this is you don't need to compute any factorials. You just do addition. You just do addition a bunch of times, and that's why it's much faster. It's really quite a beautiful pattern that this triangle exists. So that's Pascal's identity. Any questions about the statement of the identity before we prove it? Okay, let's see the proof now. So now we will count the R subsets of 1 through n in 2 different ways. Okay, so again, there's method 1, which I won't repeat. I'll just do the standard method, like from the last lecture. And what you get is that there n choose R, right? That's the definition of combinations. So I won't repeat that. That's standard. But now I'm going to count this in a sneaky second way. Okay, so here's method 2. So observe, I'm going to make 3 observations. So observe that an R subset S of the set, either it contains 1 or it doesn't, right? It's kind of a silly observation, but it's true. Every subset, either it has 1 in it or it doesn't. Okay. Now, if it has 1, then actually I can uniquely specify it by specifying the other elements, right? So if so every R subset S containing 1 is uniquely specified by a subset T of the rest of the elements. And I should say what the size of it, an R minus 1 subset T of the rest of the elements by taking S to be T union the element 1, because we know S contained 1. So there are really 3 observations, right? The first is observe that it contains 1 or not. The second is if it contains 1, then actually there's a bijection between R subsets containing 1 and R minus 1 subsets of the rest of the element. But what if it doesn't contain 1? Well, if it doesn't contain 1, I claim that I can also uniquely specify it by looking at subsets of the rest of the element, right? So every R subset excluding 1 is uniquely specified by what? So anybody have any thoughts what I'm going to write next?
R subset of T.
And R subset T of where?
Of the set 2 through n, because we've got to pick R elements of the remaining ones.
Exactly. So the picture here is that you have this subset S, and if S contains 1, then you just specify T, and T is definitely chosen from the rest of the elements, right? And if S doesn't contain 1, so if S doesn't contain 1, then this whole thing, S itself is drawn from the rest of the elements by an R subset T of 2 through n by taking S equals T. So I'm being extremely explicit and pedantic here, but I just want to make it clear. So there are really 3 observations, right? So this is 1, this is 2, and this is 3. So what's the conclusion? Well, I can apply the sum rule, right? So by the sum rule, I mean, I guess by the sum rule, the number of R subsets is equal to the number of R subsets containing 1 plus the number of R subsets not containing 1. And now I'm invoking a bijection, right? So now by these 2 observations, well, the number of R subsets containing 1. So implicitly here, there's a bijection, right? The bijection is this, or it's even explicit. But the number of T's, now I know how to count the number of such T's, right? So yeah, anybody want to, actually anybody who hasn't answered in a while want to take a shot at this? So how many such T's are there?
Would there be n-1 choose R-1?
Yeah, exactly. Because this set has n-1 elements, right? So the number of R-1 subsets of an n-1 element set is n-1 choose R-1. So that's the first term. And now the second term is the number of R subsets not containing 1. But these now are in bijection with these other T's, right? By taking S equals T. And again, this is a set with n-1 elements. So how many such T's are there?
So you're choosing all elements from n-1. So that's n-1 choose all.
Exactly. But that's what we wanted to prove, right? So now whatever we got with method 1 has to be equal to what we got with method 2 because we counted the same set of objects, right? And so therefore, this n choose R has to equal this quantity. And that's what we wanted. That's Pascal's identity. Or I'll just write as desired. I don't want to write the whole identity again. I mean, okay, that's not a very good proof style. You should write a full sentence there, but okay. So this double counting is very powerful. Okay, so there are a few more in the book. I encourage you to read Theorem 4 in the book. That's a particularly cool one. But that's it for combinatorial identities. And you have a few homework problems with this. So any comments or questions about this? Okay, so now I want to move to permutations and combinations with repetitions. Okay, so far, what have we been doing? We've been counting arrangements of objects where repetitions are not allowed. Okay. But now we're going to look at some situations where you're allowed to, take multiple copies of an object. So there are two guiding examples. The first guiding example is how many 7-digit phone numbers can be made using the digits 0 through 9. Okay, so the difference here is that now I can choose a digit twice, right? This is different from just permutations, because in permutations, I have to choose distinct elements. In this one, I don't. I can choose the same. So the difference is I can choose the same digit multiple times. Can choose the same digit many times. And implicitly, it's a phone number, so the order matters, right? Okay, so let's figure this out. This is actually easy. So the answer to this question, which is fairly easy, well, so a number is specified by the following choices, right? Well, the first choice is choose the first digit, right? So the first digit has to be in the set. Now the second is choose the second digit given the first, but there's no constraint from the first digit, right? So just choose the second digit. And then so on, just do it 7 times. So this is actually kind of boring. What's the total number of ways to choose such a number?
It's 10 to the power of 7.
Yeah, because there are 10 options. There are 10 ways for each of these steps, right? Because there are 10 digits. And by the product rule, there are 10 to the 7 ways. So this is actually kind of boring. There's nothing new here. It's not hard. It's actually easier if you allow repetitions. So in general, and our permutation with repetitions, I guess, is that so terminology here gets a little bit annoying, but let's just say, and our permutation of an object, or I don't, yeah. Our permutation with repetitions of 1 through n is just, it's just a sequence of R elements of n. Which not necessarily distinct. And the number of them is always just n to the r. So this is actually really easy. It's even easier than just permutations. Because really, all this is this is really just a function from the set 1 through r to the set 1 through n, right? Right? Because the sequence, let's say A1, A2, all the way up to AR, you know, specifying a sequence is just a function f from 1 through r to 1 through n. And you know, you've already done this on the homework and everything. So this is actually not that interesting. The interesting thing is what happens when you do combinations with repetitions. So let's look at a second example. So here's the second example. The example is how many different ice cream sundaes can be made with 5 scoops, where each scoop is one of 3 types, is either mint, chocolate, or vanilla. And I don't want to keep writing these long words, so I'm just going to call these M, C, and V. Okay. So now this is interesting because, you know, what are the interesting features of this? Well, first of all, repetitions are allowed. You can take two mint scoops, right? But the interesting thing now is the order doesn't matter, right? Any 2 mint scoops are the same. It's not a different sundae if I take a mint scoop, then a chocolate scoop, then a mint scoop, or if I just take 2 mint scoops and then I take a chocolate scoop. The order of the scoops doesn't matter. So this is the key difference here. So before I tell you how to do this, let me show you what happens if you try to solve this using the rules we came up with so far, the product and sum rules and so on. Any questions about what the statement of the problem is? I mean, okay, just to show you, for example, for 2 scoops, the options are mint, 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 or sorry, I can just list all the options. I mean, so I'm listing a different problem here, just to make sure we're all on the same page. I can do mint, mint, chocolate, chocolate, vanilla, vanilla, or I can mix them up. I can do mint, chocolate, chocolate, vanilla, or vanilla, mint, and there are 6 ways. But I'm asking for 5 scoops, and that's obviously a lot more complicated. But here the order doesn't matter. The key is that mint chocolate is the same as chocolate. Okay, so let's see what happens if we try to do this using using the division rule. So the natural thing to do is, order doesn't matter. Let's count the ordered ones and then use the division rule. Okay, so idea, count ordered sundaes and use the division rule. Well, okay. Let's draw a picture. So our flavors are mint, chocolate, and vanilla. And here I'm going to write down ordered sundaes, and here I'm going to have unordered sundaes. So if I have all mint, then I have M, 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 M. And there's only one ordered sundae with all mint, and there's only one unordered sundae. But now, let's say I consider sundaes with 4 mint scoops and 1 chocolate scoop. Well, the number of ordered sundaes that has that distribution of mint and chocolate, there are actually lots of them, right? There's MMMMC, there's MMMCM, MMCMM, MCMMM, and CMMM. And now all 5 of these actually map to the same unordered one. I mean, okay, it's not a very good picture. Let's. And then it gets even worse, right? If I now look at 3 mint and 2 chocolate, can somebody tell me how many ordered sundaes there are that have that many mint and that many chocolate? How many different ways are there to order M and C in a string with 5 symbols?
I think 10.
How did you get that?
If you have like 5 possible places to put one of the one that had 3, it's just 5 choose 3.
Yeah, 5 choose 3, which I think is actually 10. Now, the bad thing here is you can't use the division rule. Why can't you use the division rule?
Because you don't have any consistency.
Yeah, that if you think of these as being the sheep and these as being the legs, then different sheep have different number of legs, right? This has there's 1 ordered corresponding to this unordered. There are 5 for the other one. There are 10 in the last one. And it gets kind of wild. So you can't use the division rule because different sheep have different number of legs. So what you need is you need a new way of thinking about this collection of objects. And we're running out of time, so I'll leave you on this cliffhanger and we'll do it next time. So that's it. Any questions, comments?
Wait,
Is it okay? Okay, go ahead. Go ahead.
So like for 4M and 1C, if it's older, there are like 5 ways, but if it's not, only have 1 way.
Yeah, so the point is that, we're trying to count sheep here, right? We're trying to count unordered sundaes. And we were hoping that we could somehow turn it into a problem of counting ordered sundaes, then divide by the number of orderings per Sunday, right? The problem was that these orderings turned out to be different for the different unordered sundaes. So we can't use the division rule, right? If you want to count sheep by counting legs, then all the sheep better have the same number of legs each, right? Does that make sense?
So for picking 3 from 5 items is 10. So like why is it picking 3 things from 5?
Oh, because I'm picking the positions of the 3 mint.
Could you explain that again? What is that?
Yeah, so this is the number of strings of length 5 with 3 M's and 2 C's. And we already discussed that, how do you uniquely specify such a string? Well, one way is you specify the positions of all the M's. And that's just a subset of the positions 1 through 5, right?
Oh,
That's 5 to 6.
Oh, so you only like pick 3M.
Yeah, I mean, maybe you're thinking that this is the same as picking 2 C's, right? It is.
I mean, like if it's so, it's 10 for this combination. It's actually only 1 for the other.
That's right.
I mean, on the repetition side.
Yeah, and the problem is that these 3 numbers are not the same, right?
Yeah. Oh.
The number of
I
orderings
see.
is changing depending on the.
Yeah.
So
Well,
that's why we
the
can't use the
repetition
division
rule
rule.
doesn't work. Yeah.
Yeah.
Got
So
it.
different sheep have different number of legs.
Thank you. Got it.
May I ask a clarification question
Yep.
about the quiz?
Yeah, let me just stop recording.